Good morning all, and today I'm playing with opto-isolators. Now you can see here I've got two opto-isolators in a little breadboard, and I've connected the emitter of this top one to the collector of this bottom one. So here's a little close-up of the opto-isolators, and these are Sharp PC817s. So looking at the data sheet, we can see that the diode is on pins 1 and 2, the anode is pin 1, the cathode is pin 2, and the optotransistor is on pins 3 and 4, the collector is pin 4, and the emitter is pin 3. So by connecting the emitter of the top one to the collector of the bottom opto, I've created a sort of push-pull output stage. So turn one transistor on and it pulls the output up to the positive rail, turn the other transistor on and it pulls the output down to ground. But what you don't want to do is ever turn these two transistors on at the same time. Now preventing that can be quite tricky, but about 18 months ago I came up with a sort of fairly novel solution, and that is to put an additional LED pair in here, like so, and string all four of these LEDs across the 5-volt power supply. Let's just finish that off. So I've coloured the LEDs here green and red to match the green and red LEDs that I've got on my board. Now at first glance this looks like a bit of a disaster. You've got 4 LEDs strung directly across 5 volts and 0 volts. You might think that these are all going to come on, these two transistors will come on, short out the power supply, and we have a bit of a disastrous circuit. But in fact the forward voltages of these LEDs, the infrared LEDs inside the opto-isolators, I should draw boxes around these really, and the red and green LEDs, the forward voltages are higher than 5 volts. So in fact these don't come on at all. I'll put some power to this circuit and you'll see what I mean. So with 4 freshly charged Eneloop nickel metal hydrides, which are about 1.25 volts each, we've got 5 volts across these 4 diodes, LEDs, the green, the infrared, and the red, and they're not switched on. Or are they? In fact, if I dim the lights a little, you can see that they are on, but very dimly. And if I switch the battery box on and off, you can see how they just come on with a dim glow. Those dimly lit LEDs, and I'm talking here about the LEDs in the opto-isolators, aren't sufficiently bright to turn on the opto transistors, and so we don't have a problem with current flowing through both transistors and shorting out the 5 volts. Now if you want to turn on these LEDs, you can see I've added here a resistor. I have to take the left hand side of this resistor either up to 5 volts or down to 0 volts. Let's give that a try. I've put a wire in here. So if I take it up to 5 volts, the red LED comes on. If I take this down to 0 volts, the green LED comes on. Now I've re-laid out the circuit to make it a little bit simpler to use. I've put 2 switches here, these little push button switches, and 2 of the 470 ohm resistors, and I've laid it out this way just to make sure that if you press both switches at the same time you don't short out the 5 volts with the switches. So once again, if I press the upper switch, the lower LED comes on. Press the lower switch, the upper LED comes on. Now why does this happen? Well, if I press this upper switch, I provide a current path through the 470 ohm resistor and down through the bottom pair of LEDs. If I press this bottom switch, I provide a current path down through the upper pair of LEDs and then down through this resistor. Now, as I say, I originally came up with this idea for driving MOSFETs. So the gate of a MOSFET is quite capacitive, And if you have a transistor pulling down with a resistor pulling up, it's an asymmetrical circuit. Yes, it turns the MOSFET gate off rapidly through the transistor, but the MOSFET gate turns on slowly through a pull-up resistor. So this is why I wanted a transistor at the top and a transistor at the bottom. But you do have this issue with having to have a circuit where you can't have both transistors turn on at the same time. And this chain of LEDs prevents that happening. Now I called it DCOI, Dual Complementary Opto-Isolator. So we've got two opto-isolators, and they're complementary in the sense that only one can be on at any one time. And this was my dual complementary opto-isolator MOSFET driver. And it had this curious side effect that it had a logical inversion. If you pulled the input high, the output would go low. Pull the input low, the output would go high. So that really explains why I'm revisiting this circuit, because it occurred to me a few days ago, could I use this as a logic gate inverter? So to test this, I've built two of these inverters on a single breadboard. They fit quite neatly. Once again, if you take the input high, the output goes low, and that occurs on both of these DCOI inverters. So now what I want to do is link the output of one of these inverters to the input of the other. Now, in this logic family, if you want to call it that, when you connect an output to an input, it has to be done through a 470 ohm resistor. Otherwise, the transistor will create a direct current path from 5 volts through two LEDs to 0 volts, and the LEDs will burn out. And I know this because it's actually happened. So here's my 470 ohm resistor connected from the output of this upper inverter to the input of the lower inverter. So if I now use the upper inverter as an input, I'll press the high switch, and this is what happens. The low output comes on, that then goes to the next inverter, and the high output comes on in this inverter. The other way around, press the low input, that inverts to high, and then in this inverter, it inverts again back to low. So yes, this works as an inverter or a logic family of inverters where one inverter can drive the next inverter. Now, this system of logic is slightly odd in that it has three states. It has what you might call a 0, if I'm going to call red 0, and I am quite tempted to call red 0. 0 then goes to a 1 in the second inverter. It has a 1, there's my logic 1, which converts to a logic 0 in the second inverter, but it also has this third state where I don't press either button, or in fact it also works if I press both buttons. And the third state is what I'm calling the tri-state. Neither side of the complementary opto-isolator gate is on, and that propagates through to the next stage. Neither side of that is on. So you've got this tri-state situation where all the gates are off. Curious. And then I came up with the rather crazy idea of linking the output of the second inverter through another resistor back to the input of the first inverter. So now I've got cross-coupled inverters. Now initially nothing happens, and that's fine, but if I press one of these switches, it latches. If I press the other side, it latches in the other state. This is a set-reset latch. So now I'm getting quite excited about this. I've got inverters, logical inverters, a set-reset latch, which actually you can set or reset on either input. Have I created a brand new logic family, DCOI logic? Now surely someone must have done this already, so opto-isolator logic? Not really. We've got opto-isolators with logic level outputs, but nobody seems to have invented opto-isolator logic. Now there must be a reason that nobody's done this, and I think it has to be one of two reasons. Either nobody's thought of it, or it's an incredibly stupid thing to do. Not quite sure which at the moment. Now, all logic families need logic gates, so I'm going to need OR gates and AND gates and NOR gates and NAND gates. And so quick front of an envelope, quite literally, design here, where I've got the two upper transistors in series and the two lower transistors in parallel. Now I can't work out whether this is an OR gate or an AND gate. I'm going to have to test it. Okay, so here's my gate. Now I can't see the output of this gate unless I put it through another inverter, and that has slightly confused the issue, but that's not the half of it. Take a look. If I work in terms of switches, 0, 0 gives me a 0, red I'm calling 0, 0, 1 gives me a 1, 1, 0 gives me a 1, and 1, 1 gives me a 1. So in terms of the switches, this is an OR gate. Now let's do it in terms of lights. So I'll start at 1, 1. 1, 1 on the switches, that is. 0, 0 in terms of lights gives me a 1. 0, 1 gives me a 1. 1, 0 gives me a 1. And what's the other one? 1, 1 gives me a 0. I've lost track of it already. And there's also a bit of an issue with propagation of the tri-state. If I have tri-state on both the inputs, then the output is tri-state. If I put a 1 on one of the inputs, or at least a green, the output remains tri-state. But if I put a red, then the output isn't tri-state anymore. The red here gives me a green here. Not sure whether this is going to be a help or a hindrance. I've got a feeling that this could actually be an OR gate or an AND gate, or a NOR gate or a NAND gate, depending on how I configure the inverting output, and depending on how I interpret the inputs, whether I look at the high on the switches or the low of the LEDs. One thing's for certain though, if you let it, this logic family starts taking over your life. And there is the intriguing possibility that with flip-flops and logic gates and inverters, you could conceivably build a computer out of this stuff. No. Oh dear, looks like I've just gone and bought another 50 opto-isolators. Cheerio!